Okay. Well, sorry about the delay. I do apologize for a little bit of a mix-up there. My name is Jeevan Perera. I'm with NASA Johnson Space Center in Houston, Texas. Originally from Sri Lanka, actually, but left when I was very young. We lived in Europe, California, and moved to Texas when I was about 12, 13. I interned here at NASA back almost 40 years ago, and I've been with NASA full time now about 37 years. Today's presentation I'm going to talk about is a case study on the Space Shuttle Columbia accident. I'll kind of give a little bit of an overview of the Space Shuttle. It retired back in 2011, almost 14 years ago. The shuttle fleet consisted of 6 different space shuttles. The first one was Enterprise. It was test flown in 1977 and only tested the atmospheric portion of the shuttle flight. It was carried on top of a Boeing 747 called a shuttle carrier aircraft and dropped to test the shuttle's capability to fly through the atmosphere. It never really went into space. There was really 4 shuttles, starting with Columbia, Challenger, Discovery, and Atlantis. But after the Challenger accident in 1986, they did build a replacement one, Endeavour. The space shuttle stack consists, and I'll have some pictures of it, the orbiter, which looks like a airplane, the external tank, the big brown tank in the middle, and the 2 solid rocket boosters. So the whole complete space vehicle contains those 4 elements. It could carry about 40,000 pounds to about 56,000 pounds of payload into orbit. And orbit consisted of about 200 to 300 miles above Earth. So it had no capacity to go to the moon, Mars, or anywhere else, just in low Earth orbit. The total weight of the shuttle consisted or weighed about I think it was 4 million pounds. That's total weight of the vehicle, the fuel, and the payload. So really, it only had the capacity to lift and deploy about 1% of its total mass into orbit. So that's a very small fraction. If you compare that to, let's say, a car or a truck that you drive around your town, if you combined all of the weight of the vehicle and compared it to the passengers and the luggage, you're probably more like 30%. 30% of the vehicle can be useful in doing what you want to do with that vehicle. That kind of explains the extreme challenge of going into space. You have to go through the atmosphere, the dense atmosphere, and also get away from gravity, Earth's gravity. Let me show a little bit of a schematic of the shuttle. On the left side, you can see the orbiter, which looks like the spacecraft. It has the flight deck and the mid deck. That's the pressurized volume that astronauts could work and live in. And that's just really the front end of the shuttle. This big, more expansive area is the payload bay. It's unpressurized, and it contained basically like the trunk or the move-in van storage area to actually take something into space or bring it back. So a satellite, let's say the Hubble telescope, could sit inside this compartment. This big brown tank here is the external tank. It provided the oxygen and the fuel for the 3 main engines in the back. They're called the shuttle space shuttle main engines. They provided about 20%, 15 to 20% of the thrust to take this spacecraft into orbit. The vast majority of the thrust required came from these solid rocket boosters, the 2 big rockets on the side. They provided the vast majority of the thrust or the power to get this into orbit. These were all reusable except the external tank, and I'll talk about that in a moment. I also talked about the shuttle carrier aircraft. It was a modified Boeing 747. It allowed the shuttle to be transported across the U.S. for either service or other transportation needs. In the early days, the shuttle used to land out in California, but always launched from Florida, which is on the other side of the U.S. And so they needed a way to be able to transport it after landing over to the launch site. Later on, they were able to both take off and land in Florida at the Kennedy Space Center. And the carrier aircraft was mainly used to shuttle it to service at different locations, mainly in California. Once it landed at Kennedy Space Center, there was a facility, a big, you could call it a garage. It was called the Orbiter Processing Facility. That allowed the shuttle to be refurbished and be readied for the next flight. It took about 3 months after landing to be able to recondition or refurbish the shuttle. A lot of the tiles on the underbelly of the shuttle would require replacement. There was a lot of inspections that went on and repairs, so it wasn't like a commercial plane that you could land and within an hour or two be back up in the air. The Once it was fully refurbished, then the shuttle was reassembled in what was called the vertical assembly building. It's still out there at Kennedy Space Center in Florida. And that's where the two solid rocket boosters, the external tank, is all assembled together on a big mobile platform and verified and tested, not with fuel, before it was transported out to the launch site. Here you can see the launch site, this big road that takes it from uh, the vertical assembly building out to the launch pad. There was actually two launch pads used by the space shuttle. The mobile launcher platform is this big platform on wheels that wheeled it from the VAB to the launch pad. At liftoff, what they did was they fired the three main engines, the space shuttle main engines, and the solid rocket boosters to provide enough thrust to lift off Earth. These space shuttle main engines, you could gimbal or change the thrust vector. You could also throttle, increase the thrust or decrease the thrust. But these big solid rocket boosters, once you lit them, there was no controlling how much thrust you got or the ability to turn off the thrust. It was almost like a fireworks, a bottle rocket that's launched. Once you light it, it burns till it's done. So what they would do is fire the three main engines, ensure that they performed optimally, and if they didn't, they shut down those engines and scrub the launch. But if all three engines fired optimally, then they would launch the two big rockets, and at that point, the shuttle would lift off. About 2 minutes into the launch, the uh, shuttle's solid rocket boosters would be completely emptied, and so they would be ejected away, and there was a system that allowed a parachute to pop out and gently land the solid rocket boosters in the ocean, and they would be refurbished for another shuttle mission. So 2 minutes into the flight, the only thing that are burning are these three main engines and the external tank that contains the fuel and the oxygen. About 7 minutes later, so 9 minutes after liftoff, even the external tank is fully emptied. And at that point, about 9 minutes into the flight, the shuttle just coasts into space. And if nothing was done, it would re enter on the other side of Earth like a ballistic missile. And what they had to do was add a little bit more velocity to the shuttle to be able to circularize the orbit around Earth instead of coming back to Earth. And they did that with two smaller engines called orbital maneuvering system engines, OMS engines, and they would add some velocity to the shuttle so that it would start to orbit around Earth instead of coming back. The fuel and the oxygen in the big external tank would have been um, ejected away. the fuel and the oxygen for these two little engines are in these big pods. In addition, there was about 45 smaller engines called reaction control system engines. You can see three of them there. You can see um, a few up here also. What those were used for is to change the attitude, either the pitch, the yaw, or the roll, or the translation in the X, Y, and Z directions once you're in orbit. Unlike a aircraft that can use the control surfaces like the rudder and the ailerons and the flaps to change the attitude, when you're in space, there's no air flowing over the control surfaces, so they would do nothing. So these little rockets in combination could change the attitude or the direction of the shuttle once it's in orbit, mainly to be able to dock to something like the International Space Station, to come close to a satellite that they're going to repair, or whatever the mission required. It also allowed the shuttle to be able to flip and go in a backwards direction, because when the time came for it to return, they would have to fire these two smaller OMS engines to be able to slow the orbit down to, to bring it back on a trajectory back to Earth. Here you can see the payload bay door opened with the satellite to be deployed or a satellite to be serviced. You can see the big robotic arm that was controlled by an astronaut inside the flight deck. So as I said, when the mission was over, 7 to 20 days later, the shuttle would flip and go backwards and use the engines to slow itself down, and then flip itself back the right way and re-enter. The shuttle is going at an extremely fast speed, 17,500 miles an hour. That allows the shuttle to go around Earth in about 90 minutes. It could cross the United States in about 5 minutes, where a commercial plane would take 5 hours to make that journey. So these, on re-entry, there would be extreme temperatures because of the frictional forces that impart energy onto the underbelly, and it uses that to also slow further down to be able to be captured within the atmosphere. And then at that point, these control surfaces like the rudder and the ailerons would become effective because it was within the atmosphere and air would be flowing over them. So those control surfaces would work, and it would glide towards the runway and land like a glider. Once it landed, I think I mentioned early on, they landed in California on these big salt lake beds that had hundreds of square miles of flat earth, so that if there was any discrepancies on the trajectory, they could safely land anywhere as long as it was close. But once they got enough confidence that they could land precisely, they switched the landing site to Kennedy so it would make it easier landing and taking off at the same location. So now I'll kind of cover a little bit about the Columbia accident that occurred in 2003. These are all the crew members from that mission. They were all mainly rookies, first-time flyers, except the commander, Rick Husband. Um, they were on a mission called SpaceHab. It allowed a research module to be put into the payload bay and allow the astronauts to conduct microgravity research in here. Remember how I said this whole area is unpressurized, but they had connectors that allowed this whole volume to be pressurized and a research lab to be run over the course of about 16 days. It launched on January 16th in 2003 out of the Kennedy Space Center in Florida. It was the 113th mission of the Space Shuttle, and was not to the International Space Station, which started construction in 1999. Unfortunately, it was to conduct this science experiments in space. Uh, about 82 seconds after liftoff, there was some foam, about 1.3 pounds of foam, that broke off that external tank that impacted the leading edge of the shuttle. And let me show you the picture over here. So you remember this big external tank? It's cryogenic. It needs to be kept at very cold temperatures to keep a stable state in liquid form. So they have this insulation that they spray on. That's why the tank is brown. And there was a piece of the foam that came off near the attachment point of the shuttle to the external tank that broke off and impacted the leading edge. NASA did observe this object on video, and so engineers started examining the imagery to figure out if there could be any catastrophic or dangerous conditions by that impact, not only to the leading edge, but also to the underbelly. The underbelly experiences where the tiles are experience about 2000 degrees Celsius, and the leading edge, so that's the very front edge of the wing and the tail, they experience much hotter temperatures, and so it's not a silicate tile, the black tiles. I'll show you that in a minute. They were a different material that was designed to take very, very hot temperatures. The impact was in that area, and some of it looked like it impacted the underbelly, and I'll show you that also. The engineers started doing mathematical analysis using some of the tools and software that they had to assess how bad the damage could have been. They had experienced these kinds of foam breaking off and hidden the shuttle, and there had been no severe consequences of those impacts. And so, even though there were some engineers that were very concerned, others and managers weren't as concerned. And the mathematical models indicated that it didn't create much damage and that there really wasn't any concern. But there were still engineers that were still concerned, and so they talked about reaching out to the U.S. military, the Department of Defense, because they have a lot of spy satellites in orbit, and they were going to request the military redirect those cameras towards the shuttle so that they could get a close-up view of the outside of the shuttle to see if there was any damage that could be of concern. So there was initial dialogue with the Department of Defense, the U.S. Department of Defense, mainly the Air Force, to try to get some of the spy satellites to take pictures around the shuttle to see if there was the damage. But because there was feedback that the software indicated, the analysis software, that there really wasn't much of a concern, and it did require quite a lot of coordination and approval, eventually the management team decided to drop the request from the military to get those more detailed images. And by about flight day 8, the mission control team talked to the shuttle and commanders and told them, of what had happened and what their analysis had indicated, and that there was no concern for damage to that material at the very front leading edges is called reinforced carbon-carbon, or RCC, or the tile, the silicate tiles, the black tiles on the underbelly. Let me show you that also in an image of the shuttle. Here, the underbelly, you can't see it too well. It's all made out of very lightweight ceramic or silicate tiles. But at the very leading edge, so the very front edge of the wing, the nose tip, and the leading edge of the tail, where the most heat is generated on re-entry, it is made of that other material called reinforced carbon-carbon. You can see it here a little bit better, this whole section in the front and this section in the front of the tail. So the mission continued, and on flight day 16, it began the process of re-entry into Earth. Ironically, on the 13th day of the mission, There was a moment of silence by the crew to honor the Apollo 1 astronauts, the ones that died during testing on the ground back in 1967, and the Challenger. All of those happened to also occur in January. And so there was a moment of silence. And then 3 days 3 days later, they began the sequence of re-entering and return to Earth. They're going at about Mach 24, so 24 times the speed of sound as they re-enter. And it starts to fly over California, and that is during the peak heat-in period of the shuttle as it's coming in really fast through the atmosphere. A few minutes later, there was signs of debris as the shuttle broke up around 2,300 feet above Earth. That's about 70 kilometers. Uh, the thermal tiles were starting to shed, and then we lost communication a minute later. Here is a little closer view of the shuttle. This is the piece, a little bit of the foam that was here had broken off and impacted this reinforced carbon-carbon material at the front. As I said, that material was designed to take very, very hot temperatures, but not take any kind of impulse loads, forces that it wasn't structurally designed to take any kind of impact, substantial impact. Here you can see a little closer view of that bipod ramp. Here, there's a still image of the piece that broke off and impacted right on the leading edge. And that leading edge of the wing is depicted here, and computer analysis indicated that as it broke off the bipod ramp, it impacted the 7th and 8th section of that reinforced carbon-carbon. Here, there's a map of the U.S., and it may not make a lot of sense to those that have not been to the U.S., but California is on the West Coast. The next state over is Nevada, then Utah and Arizona, and the first pieces of fragments started breaking up here as tiles broke off, pieces of the wing. And then New Mexico, and then you have Texas here. The vast majority of the debris broke apart and landed over the edges of eastern Texas and Louisiana. And if you kept going forward, you would have um, Mississippi, Alabama, and then Florida where it would have landed. Here you can see some images from the ground of the breakup. They were able to recover about 40% of the orbiter, and here they reassembled it in a big hangar to understand and determine the root cause and the elements that led up to the accident. So that's part of any accident investigation, including aviation. I've got a video right here that shows a ground test. They took that same reinforced carbon-carbon material, there were spares for the shuttle, and shot a cannon with the foam, about 1.3 pounds of foam in the same dimensions. And the relative velocity of that foam hit in this would have been about 500 miles an hour. That's about 800 kilometers per hour. So I'm going to play the video, and you can see this foam during a ground test that was done subsequently to see the impact of that damage. So let me play it. Here you can see it, and you can see it bounce off and create a big hole in the wing. And here we can see it from the inside, same test, but from the inside of the wing. So about 80 seconds after liftoff, there would have been a big hole in the wing. And as it re-entered Earth, and the hot plasma from the very hot temperatures that were forming during re-entry all of that hot plasma would have seeped into the wing and melted the metal structure, the aluminum structure, and then um, diminished the structural integrity of the wing, which would have broken apart. And then once the wing broke apart, there would have been no control stability for the shuttle, and it would have tumbled and broken apart completely. There was an accident investigation report soon after. They was formed by leading experts, and it was commissioned by the president, President Bush, back in 2003, soon after the accident. The team that investigated the accident determined what the root causes and what changes NASA had to make to um, restore the flights of the shuttle. So the key findings that they found were that systematic cultural issues with the organization NASA as the culture of NASA and how they managed large programs, that it lacked effective decision making in critical areas. It didn't have sufficient risk management practices or communication. And so they outlined a bunch of requirements that they levied on NASA to correct before the shuttle could fly again. They wanted to improve the technical excellence of the teams. Some of the models that they used for analysis after they saw the video were not sufficient, and they didn't understand fully, or it didn't model fully, the physics of the motion of that debris and how it would impact and damage the shuttle. Uh, they also cited that there was not a full, complete understanding of this very complex vehicle and system, that there wasn't enough independent engineering and technical oversight, that the program management team for the shuttle had schedule pressures that forced them or encouraged them to launch maybe not at the appropriate times, and that there wasn't enough of an independent oversight to make sure that the program management team was making the right decisions. The same thing from the systems engineering and integration side, that there wasn't an independent team of engineers that could provide adequate systems engineering and integration functions to the program, and that there was lacking adequate modeling and analysis and assessment tools needed to effectively and safely run the program. I think with that, I will end, and I'll leave the last bullets here and open it up to any questions that you have related to the accident, about NASA, or anything about engineering in general. I have maybe about 8 minutes or so. Is there any questions from the audience? Read it out. Yeah, that would be great. Okay, let me get back to the, yeah. Okay, yeah, now I can see it. Okay. I don't see the text. Is that going to show up somewhere? Okay. Let me look at the chat box. Okay. Yeah. So the question was related to how does it keep a specified flight path? Uh, the software is actually what controls the shuttle. It's not the pilot or the commander that guides the shuttle back or even into orbit. It's all done by the onboard flight software systems that control the guidance, navigation, and flight control all the way up into space and back down. The shuttle was very unstable aircraft because of its mission, and so humans would not be able to uh, adequately control it safely into orbit or back down. So this flight software takes inputs about speed, pressures, temperatures, and trajectories and makes adjustments to the control surfaces or to the rocket engines to be able to fly a specific safe trajectory into orbit and back down. And so it's all controlled through the software. Okay. Are you reading that or is, oh, I see it now. So the question is, how can we join NASA as an engineer? Are there any specific programs or certifications that we have to complete? And would like to hear your story. Oh, okay. I'll explain that. So unfortunately, NASA is a government agency of the U.S. government, and so you have to be a U.S. citizen to be able to be a NASA engineer or manager. There are many contractors like Boeing, Lockheed, SpaceX. I think most of them do not require U.S. citizenship, but at least U.S. permanent residency or green card. So to work for the U.S. government or U.S. companies, you would have to somehow immigrate to the U.S. to be able to be hired on. Um, NASA hires pretty much most engineering, mainly aerospace engineering, mechanical engineering, electrical engineering, computer science, biomedical engineering, chemical engineering. So there's lots of different types of engineering that they hire. They do hire interns. So when you're in university, you can hire on as an intern if you get selected and work as you're studying. And then when you graduate, there's a better chance that you can be hired on full time, either by a NASA contractor or by NASA itself. Um, One way I would suggest if you have interest to work for a U.S. space company or even NASA, the space agency, is if you do your undergraduate degree or your graduate degree in a U.S. university. So you have to apply for a student visa and get accepted to a university. Um, a lot of times, your student visa will allow you to get internship experience and then practical experience for a year or two after graduation. And lots of engineers that are foreign born like me, that's how we did it. Is came here on visas and then were able to stay and then work and then eventually get your citizenship. My personal story is that I think I mentioned I'm originally from Sri Lanka. My dad was in the Sri Lankan Navy and was selected to study out in California at the Naval Postgraduate School, U.S. Navy school, and came back to Sri Lanka. And then he was able, when he retired from the the Sri Lankan Navy, we immigrated to England and uh, were in Europe for about 5 years before we eventually immigrated back to the US when I was about 12, 13. So by the time that I was in university, we had got my citizenship from permanent residency, and I was able to get an offer from NASA when I graduated from undergrad in aerospace engineering. Subsequently, I did get a master's and a doctorate in engineering and also a law degree that I use sometimes. So I went to law school and passed the bar, the Texas bar. Any other questions? Okay, how does NASA balance innovation and safety when developing new spacecraft like the Orion or Starliner? So, yeah, Orion, for those that don't know, is a NASA-owned vehicle that was the replacement vehicle for the Space Shuttle. So when the Space Shuttle retired in 2011, the intention was to um, replace it with a new NASA spacecraft called Orion, which was more like a capsule, uh, kind of kind of the traditional spacecraft, manned spacecraft. That was the contract to build that was Lockheed Martin, a U.S. aerospace company. But about that same time, when it was supposed to come online, uh, the there was a change in direction by NASA. Instead of NASA procuring and building and owning a spacecraft, the thought was that we would rent access to space like an Uber. Instead of owning the vehicle, we would rent the vehicle. And that's where Starliner, which is the Boeing commercial crewed spacecraft, and then also the Crew Dragon, the SpaceX. NASA contracted with both companies not to build a spacecraft for us, but to build it for themselves, and we would guarantee that we would buy seats for access into space for our astronauts. And so that started, the contracts went out around 2010, and SpaceX was the first that was able to deliver safely crews into space. They own that spacecraft, and we just rent or buy seats to take us up and then seats to take us back down. Orion is supposed to now be focused on lunar and Mars missions. The first crewed missions back to the moon will be the Artemis 2 using the Orion next year sometime. They won't actually land on the moon. They'll be on a 20-day mission around the moon, very similar to the Apollo 8 missions. And then Artemis 3, which would be a year or two later, will actually bring back crews to the lunar surface. And then eventually we would set up permanent habitation for long-term science and research on the lunar surface, which will lay the foundations for us to go back, not to go back, but to go to Mars. Um, Many of you may know that a trip to the moon and back is about 3 days in travel time, traveling really, really, really fast. It still is a 250,000 miles away. But because of the distances, Mars missions would take about almost 2 years of travel time in both directions. And so that is an extremely risky and dangerous mission. And so they want to use the lunar surface and lunar outposts to be able to build the reliability and the safety to be able to mount a Martian mission, which again, for only a 30-day stay on the Martian surface, it would take about 2 years total trip time. I'll have time for maybe one more question. Can we join NASA as a planetary scientist or a cosmologist? And what is the path for qualifications? I think, again, if you want to work for NASA, you would either directly for NASA, you'd have to be a U.S. citizen. If you want to work for a U.S. company, you'd have to be a citizen or a permanent resident of the U.S. NASA does collaborate with foreign space agencies, and so there are options where you would work for a foreign space agency that has collaborating with NASA. And so, in essence, you get to work with NASA indirectly, and you don't have to be obviously a U.S. citizen or a U.S. permanent resident to work for a foreign space agency. So the last question was, why is NASA not building rockets now, but outsourcing it to private companies? I think the main philosophy there is that we realize that in order to really drive down the cost, improve safety and reliability, um, it has to be more driven by the commercial sector. This is very similar to how the US government treated aviation in the 1920s and 30s. They funded research, they purchased planes and drove innovation, but they allowed the private industry to be able to build and innovate and improve safety, reduce costs. So, in that same light, I think NASA realized about 15 years ago that routine access to space would become much more routine than it was. And in order to facilitate a safer and more cost effective way, to start spurring innovation from the commercial sector. And that's why they had a selection process to pick two companies to build the spacecraft to take humans, and that was Boeing and SpaceX. And as you can see, it is becoming much cheaper to get humans and safer to get humans into space or any cargo. And so NASA does build uh, space systems, just not the ones that take us into low Earth orbit. They're going to design and own and operate the space systems that do the exploration of the moon and then eventually to mount expedition to Mars. And so I think it's just a natural process that has occurred now that there's a lot of interest worldwide, not only from governments, but also from private corporations to be able to have lunar operations or space operations. Well, thank you for all of your time. Unfortunately, I'm out of time to address any more questions.
Thank you so much, Dr. Pereira, for that incredibly insightful and thought provoking session. As we missed the formal welcome at the start, so I would like to take this a moment to extend our deepest gratitude to you, sir, for taking
Oh,
out of this incredibly busy schedule to be with us here today. It's not every day we get the opportunity to learn directly from someone at the heart of NASA's mission. Your insights on safety, risk, and real world lessons from Columbia and beyond were truly eye opening and thought provoking. Thank you once again, Dr. Pereira, for sharing your experiences and expertise with us with such clarity, depth, and humility. It was an absolute honor to have you with us here today. Next, as we are about to conclude today's session, I would like to invite Mr. Sudhira to address the audience.
Yeah, sorry about that. Actually, sir, I just want to thank you again as the president of SEDS Ruhuna. We are trying our best to educate our undergraduates about the space exploration. So there seems to be a technical problem, so I won't take it long because I'm hosting the meeting also and speaking right now. So that's all, sir. Thank you very much for your valuable time. We really appreciate it, and we are looking forward to work with you in the future. Thank you very much.
thank you. Take care. Bye.
Thank you so much, Mr. Sudhira. That brings us to the end of the episode of Space Talk. We hope you leave tonight with new knowledge, new inspiration, and a deeper passion for space exploration. Until we meet again, keep looking up, stay curious, and never stop exploring. Good night.